In this video, I want to talk about the actual measurement of the dextrorotatory or levorotatory nature of a molecule in a polarimeter and how we define what we call specific rotation. Specific rotation is denoted with an alpha in brackets, and you'll usually see a subscript, often the letter B, which refers to the sodium D line at a wavelength of 589 nanometers, which is the standard wavelength for measuring rotations. And then at the top, you'll see a number, which is the temperature in degrees C. (22), for example, is close to room temperature. So an alpha in brackets is a specific rotation. And the specific rotation can be calculated using the formula alpha observed times 100 divided by D times L, where D is the path length in decimeters, where L is the path length in decimeters, and C is the concentration in grams per deciliter. And hopefully you remember that deci means 10 to the minus 1. So a decimeter is 10 to the minus 1, which comes from the same root as decibel, right? The decimal system, which is based on powers of 10. So it's a slightly weird concentration unit, but when you see a specific rotation in the literature, if you were to look up in the literature, for example, you were to see an alpha D20, that means it's measured at 20 degrees C with the sodium D line of plus 50.0 degrees, and then you see in parentheses C equals 8, and ethanol as a solvent. There are no units on that concentration because it's understood that when you're working in polarimetry, you're working with a concentration in grams per deciliter. This is slightly different from the equation that's in your book. The equation in your book is alpha without the 100 times C times L, and they define the concentration in grams per milliliter for pure liquids. It is actually the specific rotation alpha is equal to alpha observed over D times L, where D is the density in grams per milliliter, and L is still the path length in centimeters, or sorry, in deciliters. So the equation in your book is for measuring pure liquids, where the density is given in grams per milliliter because that's the normal unit that we use for density. Use of the grams per deciliter in the equation and putting the 100 up there, which is simply the conversion factor from milliliters to deciliters, is more useful because typically you can only dissolve approximately 1 gram per deciliter or 2 grams per deciliter in solution. Right? Most compounds are not soluble to a meaningful degree in concentration units in grams per milliliter. So which equation you use will depend on whether you're measuring a pure liquid and using the density, or a solution and using the concentration. And the 100 is necessary if you're using the concentration in the standard unit of grams per deciliter. So how is this measured, right? This is what's actually measured from the instrument. And the instrument And it generates plain polarized light and then sends that plain polarized light through your sample. So what we have is a sodium lamp, which is an orange glow. Street lights are often sodium lamps because they're inexpensive. So we have this big light source here. And then we have a polarizer prism, which takes the light, which is normally randomly oscillating in all directions, or in many planes, and converts it to light that's oscillating just in a single plane. This is our plain polarized light. We then have our sample in a chamber. It's been measured very accurately. The ones that we have in our lab are 20.00 centimeters. That's a glass tube with very flat windows on the ends. When the plain polarized light passes through a sample chamber that contains a chiral molecule, then the plane that the light is oscillating in will change. So, for example, after we go through the sample chamber, we might have light that is now oscillating in that plane and has been moved by a certain angle, alpha. So if we were to line up our analyzer prism exactly with the polarizer prism, it's no longer lined up with the new plane of oscillation. The analyzer prism is on a rotating stage, so what we can do is we can rotate that stage until the analyzer prism lines up with that plane polarized light. And then we can measure the angle of rotation that it took to take this analyzer prism and line it up so the light was going through. Right? So initially, we wouldn't be passing all of the light through that prism, but once we rotate the analyzer prism, now it's going through and we get maximum brightness. We get the maximum number of photons. There are some subtleties in the measurement of the angle for different instruments. Our instrument is actually, it's a very simple instrument. Ours was actually built before World War II in what was Vienna, which in what is now Austria. And it's a very, very old instrument, but it's really simple. Okay. Modern instruments cost about $25,000. They can work with very small samples, and they use a photomultiplier tube to actually measure the number of photons. But it's pretty simple, right? We're just going to measure the angle, alpha, by which the analyzer prism has to be rotated in order to achieve maximum brightness, maximum number of photons of the plane polarized light coming through. So we'll measure out a known mass of compound and dissolve it up in a solvent, ethanol in the example I used, fill our sample chamber with it, put it in a chamber of a known length, so we know the path length, L, in the denominator here, and we'll measure our observed rotation and come up with the specific rotation. Since the specific rotation corrects for different path length and different concentrations, we'll get the same specific rotation as long as we keep the same wavelength and temperature for a compound of any concentration that's measured. So the specific rotation is what's usually reported as the most useful number. It is very wavelength dependent though, so if you measure the wavelength that is not the sodium P line, it's not comparable, and it is somewhat temperature dependent. It's not as temperature dependent. The reason the solvent is usually listed is because it is a little bit unpredictably solvent dependent. So it's best when you're making a measurement to measure it in a solvent that's similar to the solvent that the literature reported. So since the literature reports ethanol in this case, I want to use an alcohol-based solvent. Probably not want to use benzene or chloroform. But if the literature reported a number in benzene, then I'd want to use toluene. Not benzene because it's carcinogenic, but I'd want to use a compound that's as close as possible in characteristics to the compound that was, to the solvent that was used in the literature. So let's look at an example. Let's say I have this same compound. That the literature reports as having a specific rotation of plus 50.0 degrees at a concentration of 8, measured in ethanol, in the sodium P line. And I put this compound in, and this is what I observe. And I get an alpha observed of minus 4.8 degrees. The first thing this tells me, because this is a negative number, this is the L isomer, is that I'm working with the opposite enantiomer from the one that was reported in the literature. So I have the other mirror image isomer. If that's the sodium lamp that I'm working with, I put D on there. If I'm measuring it at room temperature, hopefully my temperature is similar to 20 degrees. Maybe it's 22 degrees in here. And now I'm going to set this equal to alpha observed times 100 over L times C. I'm measuring this in a 20 centimeter cell, which is 2.000 decimeters. And let's say that I made up a solution of 2.000 grams in a 25.00 milliliter volumetric flask. Our sample chambers have a volume of about 12 milliliters, which means a 25 milliliter volumetric flask is the lowest logical size for measuring. Which means my concentration is equal to 2.000 gram over 25.00 milliliters times 100 milliliters in 1 deciliter, which, since 100 over 25 is 4, is a concentration of 8, which is identical to what the literature reported, and often it's convenient to measure it at approximately the same concentration. So this is 8 grams, or 8.000 grams per deciliter. And I measured this at minus 4.8 degrees. usually measured in two significant figures, so or two decimal places, so let's say it's minus 4.80 degrees. So in the numerator, I have 480. And in the denominator, I have 16. 0.00. So I've got 4 significant figures in my concentration. I've got 4 significant figures in my path length. Actually, I only have 3 in my numerator, so I'm only going to have 3 significant figures when I'm done. So the observed rotation is minus 30. Oh, sorry, the measured specific rotation is minus 30 degrees. And I measured it at a concentration of 8. And let's say I do this in methanol. So what I would report for my measured specific rotation would be alpha D 22 is equal to minus 30.0 degrees, C equals 8, and methanol, this is measured. That's a smaller number, in addition to being in the opposite direction, than was reported in the literature. This compound is not just a single enantiomer. Let's assume it's chemically pure. It is not optically pure. We can describe the optical purity which is also referred to as the enantiomeric excess, that's the convenient abbreviation EE, as being equal to the measured specific rotation divided by the specific rotation of the pure sample which we generally take as the largest number available in the literature. That might not actually be 100% pure sample either. There are many examples where early literature reports fairly small specific rotations, and then later literature reports larger number because people achieve a greater optical purity. But it's equal to the measured specific rotation divided by the pure specific rotation. Brackets denote specific rotation. The alpha observed had no brackets. Times 100. Right, so converting to a percent. So in our case, the optical purity, or the EE, would be equal to minus 30 degrees, 0.0 degrees, divided by plus 50.0 degrees. And in both cases, we take the absolute value. So we always end up with a positive number, times 100. Or 60.0% EE. 60% optical purity. What does that actually mean? Well, the name enantiomeric excess tells you. A one-to-one mixture of two enantiomers does not rotate toward polarized light, and is referred to as a racemic mixture. and a chiral molecule, right, a molecule that is not capable of rotating plane polarized light in the first place because it doesn't have a non-superimposable mirrored image, will not rotate plane polarized light either. But this is a mixture of one enantiomer that's trying to rotate the plane polarized light in one direction, and another enantiomer that's trying to rotate the plane polarized. When it hits one molecule, it moves a little bit to the right. When it hits another one, it moves a little bit to the left. And if it hits an equal number of molecules on its way through the sample chamber, it will result in no net rotation. So the optical purity tells us how much excess of the dominant isomer there is after we remove the portion that's the racemate. So 60% EE means 60.0% pure L isomer. In this case, the levorotatory isomer because it's got a negative sign on its rotation, and 40% racemic mixture. The reason the optical rotation is only 60% of the maximum rotation for the pure isomer is because this 40% of the soil sample isn't doing anything. Right? This is a racemic mixture of 20% L isomer and 20% P isomer. So if you were to describe this molecule as a mixture of the L isomer and the P isomer, we would add these two together, and we actually have 80% L isomer and 20% B isomer. So it's an 80-20 mixture, or a 4-to-1 mixture of the levorotatory isomer and the dextrorotatory isomer. But 20% of this levorotatory isomer is busy canceling out the effect on plane polarized light of the 20% of the sample that is the D isomer, which means that only 60% of the L isomer is actually contributing to the overall net rotation. So the optical purity number looks worse than the actual ratio, right? Because we're only counting the excess, the amount of the pure isomer that's left after we remove the racemic mixture. So it's not a 60-40 mixture of L and D isomer, it's an 80-20 mixture of L and D isomer, but 60% enantiomer excess. So the question I would usually ask you next is, well, which is the dominant compound, the R or the S stereocenter? And the correct answer to that question is get lost. You're not fooling me with that nonsense, because there is no relationship between a levorotatory or a dextrorotatory isomer in the actual measured optical rotation and the three-dimensional arrangement of the atoms that refer to the rectus or the sinister orientation in the R and S nomenclature. The subject of the next video will be how to look at a three-dimensional structure of a molecule and determine whether the chiral center is R rectus or S